So let's solve this question. Let z be a complex variable if f of z is equal to sin pi z by z square into z minus 2 and c is the cycle in the complex plane with mod z is equal to 3, then cyclic integral over c f of z dz is dash, of course. Okay, so let's see solution. Given f of z is equal to sin pi z divided by z square into z minus 2, of course. Okay, so now let's see this expression is what you have, of course, sin pi by z by z square into z minus 2, and c is the cycle in the complex plane with mod z is equal to 3. Fine. So let's see, you have the cycle with complex in the complex plane with mod z is equal to 3, of course. Fine. Okay, so this is mod z is equal to 3. So this is 0 ultimately, and z minus 2. So 2 is somewhere here. So this is 2. So both the points are lying inside the path, and let's say we'll evaluate it in the counterclockwise sense, of course, so that because nothing is mentioned, so we can take it by default. So let's see, by Cauchy's residue theorem, we can apply Cauchy's residue theorem. Cauchy's residue theorem, both the poles are falling inside by Cauchy's residue theorem, of course. So what we can have is f in cyclic integral over c f of z dz is equal to 2 pi I times of 2 pi I times of, they have mentioned I, right? Okay, so j they have mentioned in the options. So 2 pi j times of residue of f of z at z is equal to 0 plus residue of f of z at z is equal to 2. That's it. Okay, so now we have to calculate what are the residues. So first of all, taking z is equal to 2, it's a simple pole. So residue of f of z at z is equal to 2 is equal to sin 2 pi divided by 2 square. So this gives you 0, of course. Okay, because sin 2 pi will actually give you 0. Okay, so that's 0 straight away. Now coming to the cyclic integral of this guy, residue of f of z at z is equal to 0. So this is a pole of order 2, so which is equal to 1 by m minus 1 factorial limit z tends to 0. So if this is a pole of order 2, then the first derivative d by dz of sin pi z divided by z minus 2, this is what you have here. Okay, so this is the residue, right? Because if you calculate the residues, we have 1 by m minus 1 factorial limit z tends to that particular z naught, then the m minus 1th derivative of this combination, right? So if you simplify this, it is 1 limit z tends to 0, of course. So derivative of this term, this gives you z minus 2 into pi times cos pi z minus or plus minus sin pi z, of course, this value divided by z minus 2 whole square. Okay, so if you put z equal to 0, let's see what does this expression gives you. So this expression gives you, when you put z equal to 0, ultimately this is minus 2 into pi into cos 0 is 1. When you put sin 0, this is 0, this is divided by 4. So this is minus pi by 2. So the residue here is minus pi by 2. Therefore cyclic integral over c f of z dz is equal to 2 pi j times this residue is 0 plus this residue is minus pi by 2, of course. Okay, so this gives you minus pi square j is the correct answer. So therefore cyclic integral over the c f of z dz is equal to minus pi square j is the right answer in this case. Okay, this is just the residue theorem we have to apply, and once you apply the residue theorem, ultimately this is the expression. Okay, you can see, just I'll give you a hint here. For a pole of order m, I'll just give you a hint. For a pole z is equal to z naught of order m, residue of f of z at z equal to z naught is equal to 1 by m minus 1 factorial into limit z tends to z naught of z minus z naught whole power m times f of this derivative, sorry. So nth derivative, m minus 1th derivative into of z minus z naught whole power m into f of z actually here. Okay, so this is the residue. So if you apply that, we get minus pi square g, of course. So minus pi square j is in the option D clearly. So minus pi square j is the correct answer in this case. Thank you.